Hi, Mom. Today I'm going to talk about the drag of an aircraft. So, the drag in an aircraft refers to the aerodynamic force that opposes the aircraft's forward motion through the air, and it is one of the key aerodynamic forces acting upon an aircraft alongside lift, weight, grav- gravity, and thrust. First, we have the parasite drag, and this drag is composed into three parts. We have the form drag, the skin friction drag, and the interference drag. So first, moving to parasite drag, it is a type of aerodynamic drag experienced by an aircraft due to its shape, structure, and various non-lifting components as it moves through the air. It is a result of the resistance the aircraft encounters due to its form, surface features, and the friction between the aircraft's surface and the air. So the parasite drag can be minimized through various means such as aerodynamic design, improvements, ensuring smoother surfaces, reducing unnecessary protuberances, and streamlining the overall shape of the aircraft. Minimizing parasite drag is essential for enhancing an aircraft's performance, improving fuel efficiency, and increasing its overall speed and range. What is form drag in an aircraft? So, form drag in an aircraft is a component of parasite drag which results from the shape and the structure of the aircraft as it moves through the air. It's the resistance generated by the aircraft's overall form or shape as it interacts with the air. This type of drag occurs because the aircraft shape causes disruptions in the airflow, creating areas of high and low pressure and around the structure. The variation is pressure in pressure leads to resistance impeding the aircraft's forward motion. So, second, we have the skin friction drag in an aircraft. It is a type of parasite drag that arises from the friction between the aircraft surface and the air as it moves through the atmosphere. It's caused by the resistance generated due to the interaction between the moving air and the surface of the aircraft. When air flows over the surface of an aircraft, the molecules of air that come into contact with the aircraft surface are affected by the surface irregularities and roughness. So, reducing skin friction drag is essential for enhancing an aircraft's performance and fuel efficiency. Advanced materials, surface treatments, and aerodynamic design considerations are employed to minimize this type of drag in order to increase an aircraft's speed, range, and overall efficiency. Third, we have the interference drag. It is in an aircraft a type of parasite drag that occurs due to the interaction and interference between various components or structures of the aircraft as it moves through the air. When different parts of an aircraft such as the wings, fuselage, control surfaces, or other elements come together, they can create disturbances in the airflow that lead to an increase in drag. As air flows around an aircraft, the interaction between different components can cause disruptions in the airflow pattern. These disruptions often result in pockets of turbulence, changes in pressure, or eddies that increase resistance and drag on the aircraft. These areas or interference can be particularly pronounced at joints or areas where two distinct structures meet. Moving on to induced drag in an aircraft. So, induced drag is one of the two primary components of drag experienced by an aircraft. It's a consequence of the lift producing action of the wings. When an aircraft generates lift, it creates vortices at the wingtips. These vortices induce a rear forward force that opposes the aircraft's forward motion, causing induced drag. So, induced drag cannot be entirely eliminated as it's a consequence of generating lift. Pilots and engineers work to minimize induced drag by optimizing the aircraft's performance through factors like flying at the most efficient airspeed and angle of attack, as well as employing advanced wing designs and configurations to reduce the creation of vortices at the wingtips.
Hello everyone, this is Manligjez, and now I'll be discussing about the first force that acts on an aircraft, which is the lift. Lift is the force that makes an aircraft go up into the sky. It is created when air flows over and under the wings. The shape of the wings makes an air above move faster than the air below. This faster air on top creates a kind of suction that lifts the aircraft into the air. For example, think about a paper airplane. When you throw it, the shape of the paper's wings helps it stay for a while. That's the lift in action, just like on a real airplane. The airfoil shape of the wings also plays a major role in generating lift. The design of the airfoil, with its curved upper surface and flatter lower surface, is what enables the wing to create pressure difference that produces lift. The shape of the airfoil is essential for efficient lift production and determines how well an aircraft can fly. High pressure air beneath the wing pushes it upward, while lower pressure air above the wing also contributes to the lifting force. The pressure difference between the top and bottom of the wing is what makes an aircraft go up and stay in the air. The lift of an aircraft is a crucial aerodynamic force that enables it to stay aloft or ascend. It is generated by the wings of the aircraft and is primarily a result of the shape and design of the wings. There are several factors that influence the lift of an aircraft. The first one is the wing shape. The aerodynamic shape of the wings, often referred to as the airfoil, plays a significant role in generating lift. The wing's shape, including the camber and angle of attack, affects how air flows over and under the wing. The second one is the angle of attack. The angle at which the wings meets the oncoming air, known as the angle of attack, affects the lift. Increasing the angle of attack can increase the lift up to a point beyond which it can lead to stall. The third one is the airspeed. Lift is directly related to the speed of the aircraft. Faster airspeed generally results in more lift, while slower speeds can reduce lift. The density of the air, which can vary with altitude and environmental conditions, affects the amount of lift generated. Thinner air at higher altitudes provides less lift. The fifth one is the wing area. The size of the wing also impacts lift. A larger wing generally provides more surface area for lift generations. Next are the flaps and slats. Aircraft are equipped with control surfaces like flaps and slats that can be extended or retracted to modify the wing's shape and increase or decrease lift as needed during different phases of flight. Next is the engine thrust. Jet engines and propellers provide forward thrust, which can affect the aircraft's speed and consequently the lift it can generate. And lastly, the aircraft weight. The weight of the aircraft affects the amount of lift required to maintain or change its altitude. The aircraft must generate enough lift to counteract its weight. Balancing these factors is essential for safe and efficient flight. Pilots and aircraft designers carefully manage and manipulate these variables to control the lift, ensuring that the aircraft can take off, cruise, and land safely. In addition, lift, in the context of aviation and aerodynamics, refers to the upward force generated on an aircraft's wing that enables it to overcome the force of gravity and stay aloft. This essential force is created by the principles of fluid dynamics and the design of the aircraft's wing. The key concept behind lift is Bernoulli's principle, which states that as the velocity of an air increases, its pressure decreases. Aircraft wings are specially shaped with an airfoil design, featuring a curved upper surface and a flatter lower surface. The aircraft moves through the air. The aircraft moves through the air. The airfoil shape and the angle of attack creates a pressure difference between the upper and lower surfaces. This difference in the air pressure results in an upward force, countering gravity and allowing the aircraft to take flight. Additionally, factors such as wing area, air density, speed, control surfaces, thrust, weight, and the center of the gravity play significant roles in the generation and control of the lift during flight. And that's all, thank you.
Welcome everyone to today's discussion on one of the fundamental principles of aviation, thrust. So, thrust is a force that propels an aircraft through the air. And Understanding its dynamics is crucial for the design, performance, and efficiency of the aircraft. So now, we're going to explore the basics of thrust, the different types of propulsion systems, and their impact on aviation. So, thrust is the force that propels an aircraft forward. According to Newton's third law of motion, for every action, there is an equal and opposite reaction. In aviation, this means that to move forward, an aircraft must expel a mass of air backward. So this expulsion of air generates thrust, the force that enables an aircraft to overcome drag and move through the air. So now, let's delve into the various types of propulsion systems that generate thrust. First, the piston engines. Historically, piston engines were the primary means of aircraft propulsion. They operate on the principle of internal combustion, where fuel is mixed with air and ignited it in cylinders to produce a reciprocating motion that turns a crankshaft, ultimately driving the propeller. Second one is the jet engines. So in modern aviation, jet engines have become predominant. They come in several forms including turbojet, turbofan, and turboprop engines. Jet engines work on the principle of accelerating a mass of air through a combustion process and expelling it at high speed, creating thrust. The third one is the rocket engines. While not as common in traditional aviation, rockets are used in space explorations. They generate thrust by expelling mass in the form of exhaust gases at extremely high speeds, in accordance with Newton's third law. Now, let's focus on jet engines, which power most modern aircraft. A typical jet engine consists of several components. First, the intake, the second is compression, combustion, turbine, and the fifth one is the nozzle. Intake, it is where air is drawn into the engine. Compression, it is where air is compressed to increase its pressure and temperature. Combustion, fuel is injected and ignited, leading to a high-speed exhaust. Turbine, the high-speed exhaust gases drive a turbine, which powers the compressor. The fifth one is the nozzle. The exhaust gases exit through a nozzle, creating a high-speed jet of air and producing thrust. So understanding these components is essential for appreciating how jet engines efficiently convert fuel into a forward motion. So thrust to weight ratio. One critical metric in aviation is the thrust to weight ratio. This ratio determines an aircraft's ability to accelerate and climb. A higher thrust to weight ratio means better performance, especially during takeoff and climbing maneuvers. Engineers carefully consider this ratio during aircraft design to ensure optimal performance in different flight phases. So, while thrust is essential for aviation, it comes with challenges such as fuel efficiency and environmental impact. Engineers are continually innovating to improve propulsion systems. Electric propulsion and hybrid systems are emerging as potential solutions, offering cleaner and more sustainable alternatives to traditional combustion engines. In conclusion, thrust is the driving force behind aviation, enabling aircraft to overcome drag and move through the air. From piston engines to sophisticated jet propulsion systems, the evolution of aircraft propulsions have been remarkable. As we move forward, the aviation industry continues to explore innovative solutions to enhance efficiency, reduce environmental impact, and shape the future of flight. Thank you for joining this discussion on trust in aviation.
Hello everyone, my name is
is Joseph Dagas, and I'm here to report about the aircraft's thrust. So, first of all, have you ever considered the invisible forces that govern an aircraft's journey throughout the skies? As we marvel at the grace of flight, we often overlook the significance of aircraft's weight, a silent yet influential factor in aviation. Weight is the downward force that the airplane must overcome to stay in the sky. A simple truth that underscores the delicate equilibrium required for safe and efficient flight. The total mass of an aircraft, encompassing its structural components like engines, the weight of the passengers, the cargo, and it eventually constitutes its weight. This force acts as counterbalance to lift, creating a perpetual struggle for dominance in the skies. The importance of managing this weight becomes evident when envisioning a small airplane with a weight of 2,000 pounds. Achieving equilibrium between lift and weight is paramount. Only when the lift matches the weight can the aircraft maintain a level flight. Deviating from this balance leads to consequences. Inadequate lift results in descent, while excess lift propels the aircraft skyward. Underlying the concept of weight is the gravitational force tethering the aircraft to the earth. This force, determined by multiplying the mass of the aircraft by the acceleration due to gravity, exemplifies the constant pull experienced during the flight. Counteracting this gravitational pull is the aerodynamic force of lift. It is generated by the wings. The symbiotic relationship between weight and lift dictates the fate of the aircraft in the vast expanse of the sky. Achieving equilibrium is not just a matter of stability, it is the essence of controlled flight. When lift equals weight, the aircraft maintains a harmonious balance, navigating the heavens in steady and level flight. However, any deviation from this equilibrium introduces an element of unpredictability, be it the ascent of climbing or the descent of descending. So, in conclusion, the invisible interplay between the weight and the lift shapes the very essence of the aviation. The delicate equilibrium required for an aircraft to stay aloft is a testament to the precision and science underlying the art of flight. As we look up to the skies, let us not only marvel at the soaring wings, but also appreciate the silent dance of forces that keeps this marvel suspended in the boundless expanse above us. So I'll be giving an example so that we can easily understand the topic. So, hypothetically, consider a scenario where an airliner is preparing for takeoff. The aircraft, with a total weight of 500,000 pounds, is loaded with passengers, cargo, and fuel. As the pilots taxi to the runway, this means that the aircraft is walking to the runway. They are acutely aware of the critical interplay between the weight and the lift. The aircraft's weight, composed of its structure, engines, passenger, and cargo, exerts a constant force pulling it towards the earth. In this case, the gravitational force, determined by multiplying the mass of the aircraft by the acceleration due to gravity, results in a substantial downward force. The challenge for the aircraft is to generate enough lift to overcome this gravitational pull. As the aircraft accelerate down the runway, the wings generate lift through their shape and the airflow over them. The pilots carefully adjust the angle of attack and engine thrust to achieve the delicate balance needed for takeoff. When the lift force equals the weight of the aircraft, the airliner gracefully leaves the ground, entering the realm of controlled flight. Now imagine another scenario. Imagine a scenario where the weight exceeds the lift generated. The aircraft struggles to descend. Its climb rate is sluggish and the plane may not reach the desired altitude. On the other hand, if the lift surpasses the weight, the aircraft ascends rapidly, potentially compromising the safety and control of the aircraft. Throughout the flight, from takeoff to cruising altitude, the eventual descent for landing, pilots continuously manage the aircraft's weight and lift. Fuel consumption, passenger movements, and cargo changes dynamically alter the weight, necessitating constant adjustment to maintain equilibrium. In this example, the intricate dance between weight and lift becomes vividly apparent. It's not just a theoretical concept, but a real-time challenge that pilots navigate to ensure the safety and efficiency for flight. As the aircraft soars through the sky, it serves as a testament to the meticulous calculations and adjustment made to harmonize these opposing forces, allowing us to traverse great distances with confidence in the distance of aviation. Thank you.
Greetings to everyone watching. We are now at the final stretch of our video about the different forces acting on an aircraft. Since everything is very well explained by my fellow groupmates, I will only give a recap about the concepts being tackled. So an operating aircraft experiences 4 forces, which are lift, thrust, weight, and drag. These forces are essential to the operation of an aircraft since they enable the aircraft to take off, fly, and land safely. So these forces are differentiated into 2, namely the positive and the negative forces. So the positive forces include lift and thrust. Meanwhile, the negative forces are the exact opposite of the positive forces, which is the weight and drag. So in aviation, positive forces enable flight and forward movement. Lift counters gravity, keeping the aircraft airborne, while thrust propels it forward. Conversely, negative forces are equally vital. Weight maintains altitude stability by balancing lift and drag aids in controlling speed and direction. Just as yin and yang find balance, these forces harmonize for safe, efficient, and controlled flight. Now, lift is the force that makes an aircraft go up to the sky. It's created when air flows over and under the wings, and the shape of the wings makes the air above move faster than the air below. Now, let's move on to the second force, which is thrust. Aircraft thrust is the force that pushes an airplane forward through the air. It's generated by engines of the aircraft. Think of it like the way a car engine powers the car to move on the road. Once again, imagine a paper airplane. When you throw it, the force with which you propel it forward is similar to the concept of thrust in an aircraft. Now, let's move on to the third force, which is weight. Aircraft weight is the total mass of the aircraft, including its structure, engines, passenger, and cargo. It's a negative force in aviation because it acts downward, opposing lift and affecting the aircraft's ability to stay in the air. So the next and last force is drag. Aircraft drag is the resistance or force that opposes the motion of an aircraft through the air. It's like the wind pushing against the aircraft as it moves. In addition, airflow causes drag on an aircraft because it creates resistance as the aircraft moves through the air. This resistance results from factors like pressure differences, surface friction, the aircraft shape, and induced vortices at the wingtips. So that is the end of our video about the different forces acting on an aircraft. We really hope you learned a lot watching our video. On behalf of my groupmates, we would like to extend our utmost gratitude for still tuning with us up until this far on this video. I am Rodolfo Siep III. Thank you for watching.